This video demonstrates how to conduct the fluid flow analysis using ANSYS. For this tutorial, CFX Pre and ANSYS Computational Fluid Dynamics Postprocessor are used. The definition of the problem reads like this. There is a mixing chamber for the fluid which has inlet 1 and inlet 2 and has an outlet. The fluid enters the inlet 1 with the temperature T1 and velocity V1. The same fluid also enters from the other inlet 2 with the velocity V2 and temperature T2. There will be a mixing of these two fluids and will be sent through the outlet. The objective of this analysis is to evaluate the temperature distribution as well as the velocity distribution which is happening across the flow path of the fluids which enter from these two inlets. Let us begin with the tutorial. Create a new fluid flow CFX analysis file. Press hold and drag it to the project schematic. Observe that the geometry is not yet loaded. Also, the mesh setup solution and results are pending. Right-click on the geometry, import any of the step file which is stored in the hard drive. Pick on the import geometry. Pick on browse. Currently, I will make use of the file which is existing in the recent file history, and the name of the file is static mixer. A right tick mark just beside the geometry indicates the geometry is loaded. Let me close the previously opened files of ANSYS. All the ANSYS open files were closed. Let us proceed for the mesh generation. Right-click on the mesh, pick on Edit. This will take us to the meshing window. We can find the attach status, which means the geometry is now loaded to the ANSYS Fluid Flow CFX meshing. We call it as ANSYS ICEM CFD. This is the geometry which has the inlet 1 and inlet 2, also the outlet. It is very important for us to define the inlets as well as outlets. We call it as defining the named selection. Under the selection filter, make sure that the surface option or the face option is selected. select the face, right-click, press hold, make it as Create Named Selection. Enter the selection name as GRS underscore inlet hyphen 01. Pick on OK over here. Similarly, rotate the geometry, select the other end face, right-click, press hold, create the named selection. Enter the name as GRS underscore inlet hyphen 02. Enter. Similarly, select the third face, that is outlet, right-click, create name selection and enter the name as GRS underscore outlet. Enter. All these three named selection have been recorded in the outline tree. Pick on the named selection over here. The naming with the specific words is very important for us to conduct the analysis without any issues. This is a key point to be remembered. We can see that the mesh is not updated for this file. Right-click on the mesh, pick on Generate Mesh. Let us not bother about the element size at this point of time. We can observe here the geometry is completely meshed. Save this file. Pick on File, say here Save Project. The file has been saved. Revisit the project file. Right-click on the mesh and pick on Update. Updating the mesh, and the mesh has been updated successfully. Check for the properties of this fluid flow file, and we can find that the system ID is CFX1. This is just for our understanding. Similarly, pick on the geometry. We have understood that the geometry is in the directory name, that is CFX-1, and the geometry file name was extracted from this particular folder. Having understood this, let us proceed for the fluid flow setup. Right-click on the setup, pick on Edit. This will open the CFX Pre. Now, we need to define the tools. Pick on Quick Setup Mode. This is the very first stage when we enter the Fluid Flow CFX. The simulation definition and the simulation data, the problem type set to be single phase. The fluid which we will make use is of water. The mesh file will be retrieved from CFX-1. Pick on Next. The analysis type is being steady state, and the reference pressure is 1 atmosphere. Select the heat transfer to be thermal energy. The turbulence is K epsilon. Select here. Next. The default domain need to be deleted. Let us add the boundaries now. Listen to this step very carefully. This is the geometry with the mesh. Right click on the boundaries, add boundary. Give the name of the boundary as GRS underscore inlet underscore CFX. Pick on the default domain. Let us give the name as -01 for the easy identification. Pick on. GRS underscore inlet. Let us say 01. Let us go ahead with this naming itself. Pick on OK. The boundary type need to be inlet of the fluid and the location should be inlet 01. This we have created in the ANSYS meshing domain. This is the named selection what we have created earlier. The flow specification, the option need to be normal speed and enter the speed with which the fluid enters the inlet 1 highlighted over here. Let us consider it enters at 5 meters per second. At what temperature? Let us consider it enters at 285 Kelvin. Now, right click on the boundaries, say add boundaries. The second boundary is going to be GRS inlet 02 and the domain is default domain. Pick on OK. We can find GRS inlet 02 has been created and now we are about to edit its parameters. Boundary type is inlet and the location I say here GRS inlet 02. Now this face is highlighted. The option is normal speed and the speed should be 10 meters per second. The temperature, let us enter 350 Kelvin. Having defined two inlet boundaries, let us define the outlet boundary. Add boundary GRS outlet. Pick on OK. The location need to be outlet, that is GRS outlet. This is the named selection which we have defined in the ANSYS meshing window. In this case, we are defining the flow, the boundary type to be outlet. Hence, we don't have to define the normal speed. We need to change the option of the flow specification to average static pressure and the relative pressure is set to 0. Select here, next. Under the final operations, the operation is going to be enter the general mode. Say here, finish. Observe, there are the arrow indications which says the fluid is going to enter from this direction as well as is going to enter from this direction. These directions are perpendicular to the selected face and at the base the fluid is going to exit. Select. the solver controls. Under the solver control, the advection scheme is set to high resolution. Change it to upwind. Convergence control, minimum iterations 1, maximum iterations 100. Under the time scale control, change the auto time scale to the physical time scale and enter the physical time scale 2 seconds. Convergence criteria, let it be as it is. Pick on OK. Once the CFX Pre analysis settings have been defined, let us revisit to the project page. Double-click on the solution. This will open the CFX Solver Manager. Make sure that the run mode is serial and pick on Start Run. This window is a graphical representation of the solution. It can be seen that the solution has proceeded and the message has appeared that the solution is completed normally. Pick on OK. Let us minimize the solution window and proceed for the post-processor. Again, we are visiting to the ANSYS project page. Double-click on the results. Now we are entering into the ANSYS CFD post-processor. We can see the named selections as well as the domains which we have defined. Inlet, inlet, and outlet. The default domain is going to be the complete geometry apart from these name selections or domains. Pick on the streamline. We are interested in understanding the flow of the fluid. Enter the name of the streamline as Inlet 001. There will be 25 points which represents the fluid flow. Under the colors, let us change the mode to variable and we are interested in the velocity. Pick on the geometry again. Enter the number of points to be 100. Pick on Apply. And it has to start from Inlet 01. Pick on Apply. That step I had missed. That's the reason there was information. When the fluid enters from the Inlet 1, this is the velocity distribution of the fluid. Let us animate this particular behavior. Pick on the animation window here. Select that animation, Inlet 001, and say play the animation. The speed of the animation can be controlled from this bar. This is how the fluid is going to flow. And the left side legend and the color contour represents the velocity distribution. Let me stop this animation and enter the one more streamline. Select here streamline. Enter the name as inlet 002. Enter. Now we are under the details of inlet 002. Number of points, enter 100. And under the colors, it should be changed to the variable and interest is velocity. Pick on the geometry again and the flow has to start from inlet 2. Pick on apply. This is the complete fluid flow which we can observe. Now pick on the animation. Select both the animations and pick on the play. This is how the fluids flow in the mixer and they interchange the temperatures, and this is how the velocity distribution is happening. The unit of the velocity meters per second 3.155 and the maximum is 18.39. This is all about the velocity distribution. Now let us talk about the temperature distribution. Stop this animation, pick on close. Pick on the streamline again. Enter the name as inlet 001. Let me add one more 0. And in this, I will change start from the inlet. The color need to be changed to the variable and select the velocity instead of velocity, temperature. Pick on apply. Similarly, create one more streamline and give the name of the streamline as inlet 0003 to pick on OK and change the start from to inlet 02. Under the colors, change it to the variable and set it as temperature. Pick on apply. Now we can find the temperature distribution of this fluid when it is flowing through the mixer. These are the defined streamlines. We have set the inlet 0001 to temperature, inlet 0002 to temperature again, and this is the velocity temperature distribution what we can see. Pick on the animate option over here. We are interested in animating inlet 1, that is inlet 0001 and inlet 0002. That stands for the temperature distribution. Animate. Let me take a cross section and study the temperature distribution more carefully. Stop animation, pick on close. Select the location and set the plane in that. Enter the name of the plane as section 01. Pick on OK. The section which will be taken should be perpendicular to the ZX plane, or it can be a 3-point. Let me go for the point and normal option. The point has to be at the default coordinate origin and it should be normal to y-axis, which means 1 here and 0 to the x. Under the colors, make it as a constant, pick on apply. When we change it to variable, we are interested in the temperature distribution and pick on Apply, and let us switch off all the streamlines. This is the cross-section of the mixer in which we are interested in the temperature distribution study. We can change this variable as pressure, velocity, or the temperature as per our requirement and interest. We are viewing the results in the CFD postprocessor in only one window. We can collapse this tree and split the windows into two parts. We can do it by selecting the options from here. Split the windows into two parts. Orient the flow process as per your requirement. For that, we need to again visit the tree. Let me switch off the section and only keep the flows. Thank you for watching this videos. For the queries, please contact me on the engineering tutors desk at gmail.com, or you can ping me on the Skype engineering tutors desk. For the training and the project related, you can contact on engineering tutors desk at gmail.com.